AP Calculus, AB, Unit 6, Day 10, Office Hours. So, I have a little free response question here. And there are some things about this that we can't totally do yet. So, going to have you guys, D is kind of the sketchy one, but I'll show you guys kind of how to do it, but just give you a little heads up. Okay, so the figure shows the graph of f prime. Usually you're going to get one of these on the AP test for response, a graph of the derivative. Negative 7 to 7. F prime has horizontal tangent lines at negative 3, which it looks like it does, 2, which it looks like it does, and 5. So I like to just mark those on there. Vertical tangent line at 3. So that kind of makes sense. All right, so I put that stuff on the picture. Find all the values of x, negative 7 to 7, at which f attains a relative minimum, justify. So we got to find relative minimums, and we got to justify the answers. So most likely going to justify relative mins with and maxes with the first derivative test for relative extrema. And we're going to have to write it out. There's not really a lot of calculations or work to show on this. So, I'd first go through here and say, all right, well, f prime is positive, it's increasing, f prime is negative, it's decreasing, f prime is positive, it's increasing, f prime is positive, it's increasing. I'm doing kind of what I've been doing. Critical point here, f prime equals 0. Critical point here, f prime equals 0. Critical point here, f prime equals 0. Now, if it's going up, increasing, then going down, this is a relative max. It's going down, then up, this is a relative min, a valley. It's going up, flattens out, goes up. This is neither. This is like a plateau. So, I actually know the answers to A and B already, but I got to write it and I got to justify it. So A is F attains a relative minimum at, we don't actually know what the minimum value is, we can't really find it, at x equals negative 1. Okay, so that's the answer, but then we got to justify it. Why? By the first derivative test for relative extrema. Okay, cool, you named it, which you should. But how does that work? Since it's all about the derivatives on the left and right being positive and negative, since f prime of x is negative to the left, specifically from negative 5 to negative 1, and f prime of x is positive on the right side, specifically on the interval negative 1 to 5. That's a really good, thorough answer. Now, by the way, free response points are worth 9 points on the AP exam. And I'll try and help you guys start to understand where you get points. This is worth part A is worth 2 points. The answer was a point, and the justification was a point. So you got to justify it. It's half the credit. B, relative maxes. Okay, well, we already have everything. F attains a relative maximum at x equals negative 5 by the first derivative test for relative extrema. How? Since f prime of x is positive to the left on the interval -7 to -5, and f prime of x was negative on the right side, specifically -5 to -1. There you go, another 2 points. So that's how you write your answers. That's how you justify them. Okay. C says find all the values where f double prime is negative. So that means like concave down, right? That's essentially what they're asking. Now, concavity is the second derivative, which is the derivative of the first derivative. This is already a graph of the derivative value. So the slope of this graph is the second derivative. So when the slope of this graph is negative, it's concave down. The slope of this graph is positive, concave up. Negative, concave down. Now, there's an issue here that'd be real easy that I almost missed. Technically, if the first derivative, if the slope is undefined, that means f double prime is undefined right here, right? So we have to actually break this up and say that it's negative here, it's concave down here, and then it's negative here, but we can't, we gotta break it up at 3. Gotta break it up at 3. So I've added all that stuff. We can use this to help us find inflection points also. So where is f double prime negative? So we say f double prime of x is negative on the intervals -7 to -3, do not include the endpoints, and then 2 to 3, and then 3 to 5. So those are all the intervals where it's negative. Now it says well, you should expect to justify your answer. Well, how do you know that? Like, you're getting this stuff about f double prime from the graph of f prime. So I want to know, since you could say f prime of x is decreasing, which means going down, is decreasing on those same intervals. And we could even say it's decreasing on the intervals -7 and -3, 2 to 3. I mean, yeah, I don't know. Yeah, I would just say on the same intervals. So you want to reference the graph, the information you have, and then connect it to what you're saying. Now, D is kind of the weird part. What value does f attain an absolute max? So you're looking for the absolute max, which means you should want to use EVT, okay? Especially to justify it. Now, first thing you want to look for is where f prime of x equals 0 undefined, because those are going to be critical points. I would write this down in your work, okay? That could get you points. And if you don't have it, it could cost you points. They want to know that you know what you're talking about. So -5, -1, 3, and 5 are all the critical points. And this is where they come from. So you want to explain at least the calculus part of it. So those are your critical points. Endpoints, we have endpoints. It said -7 to 7, right? So we have a closed interval. We have endpoints. Okay. If the derivative exists everywhere, then the original function exists everywhere, which means it's continuous. So we have what we need to use extreme value theorem. So then we would make a table. We plug them back to the original function. So -7, -5, -1, 3, 5, and 7. So that's our table. Now here's the hard part. You don't actually have a function to plug these in. But what we're doing, if you want this function, what you do is you integrate the derivative. This is something we haven't really gotten into, is integration. Or in other words, so like for instance, yeah, do we know any of the values anywhere? I don't know if we actually have a value anywhere. We don't. So we could say, well, it's going to start at C. And when you integrate a graph, it's the area under the graph. So it's really this area right here, the area under each of these chunks between these points that's going to help you figure out how much up the next one is. So let's just put some numbers on here arbitrarily. Like if we say this is like 2, then this looks like about 4, looks double. This one looks a little bigger, like 5. Maybe this is 1 right here. This might be more like, I don't know, 8. I'm just kind of guessing. They'll actually give you these numbers sometimes. They'll tell you what the area of each section is. Sometimes on free response. So what we're doing here is from -7, -5. If you integrate that, that's a positive area. So you're going to add 4 to the previous value. And then the next chunk, it's negative. So when you integrate, it's going to give you a negative value, which makes sense. The graph is going down, so we should lose 5. We're going to subtract 5 from the previous value, and we're going to get to C minus 1. And the next one, we add 8, and that brings you up to C plus 7. And then we add another 1, that brings you up to C plus 8. And then we add another 2, and it brings you up to C plus 10. And which one's the biggest? Well, here's the biggest. That's the max. Which one's the min? There's the min. And that's kind of a way that you can kind of help figure it out. I mean, if you look at this graph, it kind of makes sense. The graph goes up a bit, goes down more than it went up. So we're at a new low point, and then it goes up a bunch, and it goes up more, and then it goes up even more. So this end point over here has got to be the highest point. Now, writing that out and explaining that is the challenge. But we could it's a bit of work to justify this. So, I mean, we could say the answer, the absolute maximum, we don't know its value, so we're not going to say its value. The absolute maximum of f is at x equals 7 by extreme value theorem. By checking endpoints and critical points. And you guys should be very familiar with this phrase. All right. But it would take a little more work to kind of justify what we're saying here. You'd probably actually start referring to the areas and stuff. They might go through and say, well, f of -5 is greater than f of -7 since f is increasing on the interval -7 to -5. So that's kind of how you could maybe kind of explain it, why this one's bigger than that one. And then we could say, I don't know. So I'm not going to get too much into it. You're not going to have to worry about this on your upcoming test or anything, but just something to start thinking about. We'll talk about this again next semester. That's kind of roughly how you would do it. Let's try the one in the back. Which is going to have, I think, a problem kind of like that too. Another one, but the figure shows the graph of f prime, the derivative of the function f on a closed interval. So you have endpoints. Graph of f has horizontal tangent lines at 1, k, 3, which means the derivative is 0. Right? The function is twice differentiable. That means that the function, if it's differentiable, its derivative exists everywhere. Twice differentiable means the second derivative exists everywhere. And then they give you what we call initial condition. That's the starting value. So that's a little different than the last one. We actually get a starting value. Find the x-coordinate of the points of inflection of the graph. Give a reason for your answer. Now, don't say second derivative test. That's for relative maxes and mins. Your reason is going to be because the concavity changes, because the second derivative changes or something like that. Now I'm going to start labeling this graph. F prime is positive, so it's decreasing, or is negative, so it's decreasing. F prime is negative, so it's decreasing. F prime is positive, so it's increasing. And then we're going to look at the second derivative is positive, so it's concave up. The second derivative is negative, so it's concave down. And then the second derivative is positive, so it's concave up. So we can identify the inflection points are at x equals 1, x equals 3. But, so we're going to put that in words. So we're going to say, we might, say, okay, well, f double prime of x equals 0 undefined. So x equals 1 and 3, which by itself does not guarantee its inflection point. You need to state that the concavity changes. So we could say f has inflection points at x equals 1 since f double prime of x is positive on the interval -1 to 1. And well, how can you tell that it's positive? Because the graph of f prime is increasing. And f double prime of x is negative on the interval 1 to 3 because the graph of f prime is decreasing on the same interval. So I mean that's kind of a good explanation. I mean, to justify inflection point, you want to show that the concavity changes, that the second derivative changes signs. But then on this problem, you kind of have to convince me why you know that the second derivative is positive and negative on those portions of the graph, and you got to tie it to what's happening with what they gave you. Now that's the first one. So, and there's another inflection point at x equals 3, since f double prime of x is negative on the interval 1 to 3 because the graph of f prime of x is decreasing and f double prime of x is positive, greater than 0 on the interval 3 to 5 because the graph of f prime of x is increasing on the same interval. So I don't know. I mean, not that you necessarily need all of this every time, but this is about the most thorough, justified answer for inflection points. I mean, finding the answers is easy. Now, this was only worth 2 points, so your answer was probably, this and this was probably 1 point, and then the justification is another point. Next one is 4 points. And this says, at what values of x does f attain the absolute minimum on the closed interval -1 to 5? At what value of x does f attain the absolute maximum on the value of the closed interval? Show the analysis that leads to these answers. So this is kind of like the last one. We kind of need to know the area of each of those chunks. And I would say nowadays they usually give you those areas. Or, you could use a graphic calculator or something with a function they give you. But we don't. So we're trying to find absolute max and min. So we need critical points. So f prime of x equals 0 undefined. And that gives us x equals 1 and 4. So that's a critical point, and that's a critical point. F prime equals 0. Here, this is actually F double prime equals 0, and F double prime equals 0 there too. I wrote F prime equals 0 there earlier for the horizontals, but that'd be if it was the original graph. So 1 and 4 are your critical points. And your endpoints are -1 to 5. So then you can make a table. So -1, 1, 4, 5. But they did give you a value. They said at 2, the value is 6. So you kind of have something to base it off of that, right? So you can kind of work off that one backwards or forwards. Now, again, we kind of need the areas, you know, and I can't maybe break these up, be like, well, maybe this is like 2, and so then maybe this is like 4, maybe this is like kind of like 3 or something like that. And so if we go backwards, now here's 2 actually. So maybe we want this little area right here is like 1. So it's negative. We're going back. It was decreasing, but we're going backwards. So that means you need to add 1 to this. So it's about 7. And then we're decreasing, going backwards another 3. So we would add another 3 to this, and it would be about 10. So even though the graph's decreasing, the values are getting bigger if you go backwards because it came down from those values. If we go forward from 6, we got to subtract 4 and then maybe add another 2. So from this, you could say, well, this is the absolute max, and here's the absolute min, roughly. And then justifying it is kind of tough. I mean, the graph decreases, and then increases a little bit. So this had to be the highest point, right? Lowest point, I think, is going to be right here because it went down and went down a bunch more and then went up a little bit. So that's got to be the lowest point because that's when it stopped going down. It went down a ton. So it kind of makes sense just looking at the graph where the max and min are. But justifying it would be a little harder. I don't want to get too much into that right now. Like I said, I'll give you guys the tools for that next semester. Okay, part C, let g be the function gx equals x fx. So a lot of times they like to give you some new function that's defined in terms of function. Find an equation of the tangent line. So we want tangent line to g at x equals 2. So we need two things, right? Equation of any line, the point and slope. So the point, you should be able to just plug 2 in here, which would be 2 times f of 2, which would be 2 times, what's f of 2? F of 2 is this graph. F of 2 is -1. Well, actually, no, okay. This is original f of graph. So they gave us f of 2 as 6. So that's going to be 12. So we got our point. And then we want the derivative. So derivative this is going to involve the product rule. X times derivative of f plus f of x times derivative of x. So that's the derivative of g. And then we're going to plug 2 into it to get the slope there. Now, f prime of 2 would just be whatever the value of the graph is at 2, which is -1 right there. And then f of 2 they gave you at the beginning of the problem was f of 2 is 6. So these are actually exact correct answers. So this is going to be 4. So g prime of 2 is 4. So then we're going to write our equation in point slope form. Y minus 12 equals 4 times x minus 2. And then leave it like that. No need to change it. Point slope form is totally fine. So the points here, and this is worth 3 points. So getting this, I think that was our 2 points, and then the answer was like a point. But you don't have to worry about these finding the area in these graphs problems yet. But there you go. Good stuff.